Okay, hello everyone. So in this lesson, we'll be learning about photoelectric effect. So basically, when light of sufficient high energy is incident on a metal, light may be absorbed by the metal from which electrons are then emitted. So this is known as photoelectric effect. Next, the work function W of the surface is the minimum energy required to remove an electron from it. And the work function is related to the threshold frequency by this formula. Okay, so what is photoelectric effect? Okay, if you see, right, in a conductor, there are conduction electrons. So the conduction electrons are the one that is responsible for it to conduct current. So if you have a metal, when you heat it up, heat is actually energy. The electrons can absorb the heat energy and they can come out to the surface of the metal. So example of this would be like a heated filament. So when current flows through the filament, it heats up the filament, and the electrons in this conductor will absorb the energy and they come out as electrons. So you have a cloud of electrons around a hot filament. Photoelectric effect would be similar like this metal. The only difference is we don't supply heat, we supply energy in the form of photons. So we expose the metal to photons. When photon comes in, the photons will transfer its energy to the electrons. The electrons absorb this energy and come out as photoelectrons. So these are known as photoelectrons. They are basically electrons. So example of photoelectric effect would be like your solar cell or in your calculator. Okay, to explain photoelectric effect, we cannot use the concept of light as a wave. Okay, you see, right? When we did the experiment, right, when we shine red light, no sparks were observed, right? So from the wave theory, if we increase the energy of the red light, what we do is we increase the amplitude. Because when we increase the amplitude, we are increasing the intensity of the light. And when we increase the intensity, we are increasing the energy of the light. So basically from the wave theory, if I shine a red light and I don't see sparks, right, being emitted, what I have to do is I have to just increase the intensity of the red light. But when Hertz did this experiment, nothing happened despite him increasing the intensity of the light. He observed sparks whenever he changed the frequency of the light. So whenever he used violet light, then he observed sparks. So irrespective, whether he used low intensity violet or high intensity violet, he saw sparks. So this is where the wave theory of light fails to explain the concept of photoelectric effect. Okay, to explain photoelectric effect, let's go back to a metal. So this here are your delocalized electrons. They are known as your conduction electrons. That's responsible for it to conduct electricity. So this is your forbidden region. So the forbidden region would be where no electrons can exist. And these here are basically the electrons that comes out on the surface of the metal, either by heating it up or by exposing to high frequency radiation. So the potential energy of the electrons are basically negative value. So most of the time students will ask, why is the potential energy negative? Okay, to explain this, let's consider the case of gravity, right? Do you know that you can have any amount of potential energy depending on where you are on the surface of the Earth? So you can have potential energy here on the surface of the Earth or at sea level, right, and so on. And you can have up to a certain maximum. And what's your maximum potential energy? Would be right on top of Mount Everest. So if you are standing on top of Mount Everest, that's when you have the maximum potential energy, gravitational potential energy. So it's just like electrons, right? Inside a metal, the electrons can have any amount of potential energy up to a certain maximum, right? The potential energy, whether you're on the surface of the Earth or the potential energy of the electrons, are all measured with reference to the center. In the case of the Earth, is if gravitational potential energy, then you are measured with reference to the center of the Earth. In the case of the electron, then it will be measured with reference to the nucleus. Right? And your potential energy is increasing. All right, let's consider your gravitational potential energy is increasing. Right, the higher you go, your potential energy increases. So does that mean your potential energy is approaching an infinite value? The answer is no. All right, because if you have infinite amount of energy, you can move Earth off its orbit. Right, that's what you can do with infinite energy. So it doesn't make sense, right, that the higher you go, your potential energy is increasing and it's going to approach an infinite value. So in actual fact, your potential energy is actually a negative value. So if you calculate the absolute potential energy, it will be a negative value. Right? So the same case for electrons. This here represents the absolute potential energy of the electrons. So when I say absolute potential energy, it's with reference to how far is this electron from the nucleus. The further it is, the higher the potential energy. Okay, this forbidden region, all right. To explain the forbidden region will be this region, right? That means if you try to stand in this region, it's not possible. We are not considering an aeroplane or a spacecraft, right? If you try to stand here, it's not possible for you to stand here. So this is a forbidden region. So you can exist anywhere on the surface of the Earth. If you exist here, you can have any amount of potential energy, but your absolute potential energy is negative. You can exist here. All right. That means if you have zero amount of potential energy, you are no longer bounded by the gravitational forces on Earth, like a space rock. All right. It has zero potential energy, so it's not attracted by Earth. All right. So potential energy, the absolute value will all be negative. Okay, so forbidden region is where no electrons can exist. And once the electron has zero amount of potential energy, the electron is no longer bounded by the nucleus. It's on the surface of the metal. It's free. Okay, so let's explain photoelectric effect. So when you shine red light, the red photons, right, particles strike the electron. Nothing happens. So when you change to violet light, instantaneously electrons are emitted. So these are known as photoelectrons. So coming back to Hertz's experiment, when you shine violet light, electrons will be produced on the surface of the metal. But since you apply high potential positive, negative, the electrons that are negative charge particle will be attracted towards this positive terminal, right? So when electrons are accelerated, they emit electromagnetic radiation. So that's why you see the sparks that's moving when the electrons are emitted. When you shine red light, no electrons are emitted on the surface of the metal, so therefore there's no sparks. Okay, definition, work function. So what do you mean by a work function of a metal? So work function is defined as the maximum potential energy of the electrons. So you see, right, the electrons here can have any amount of potential energy up to a certain maximum. So in this case, the maximum potential energy of the electron for this metal will be 3 electron volts. Okay, another thing is if the electron has maximum potential energy, then it requires the minimum amount of energy to come out as photoelectrons. Right? You see, if the electron has, in this case, maximum potential energy of 3 electron volts, then it requires a minimum amount of energy to come out. If another electron that has 4 electron volts of potential energy, so this electron requires more energy to come out, right? So the closer the electron, the deeper it is inside the metal, it has lower potential energy, so it requires more energy to come out as photoelectrons. So work function is defined as the maximum potential energy of the electrons. And different metal will have different work function. Okay, next is threshold frequency. So what do you mean by threshold frequency? So threshold frequency is the minimum frequency of radiation needed for photoelectrons to be emitted. So coming back to a scenario here, assuming, right, this electron has maximum potential energy. So for this electron to come out as photoelectrons, it requires a photon, right? A photon of minimum energy for it to come out. That means the photon must have a minimum of 3 electron volts. So in other words, since there's a minimum energy of photon, this implies there must be a minimum frequency of radiation. And this minimum frequency of radiation is known as the threshold frequency. And it is related to the work function. All right, so clear about photoelectric effect and clear about what is work function. So work function of a surface is the minimum energy required to remove an electron from it. And work function is related to the threshold frequency by this relationship, right? Okay, next, the intensity of the incident light affects the number, but not the energy of the emitted photoelectrons. Okay, so what is intensity? So how did Einstein define intensity? And the next point will be the minimum frequency, threshold frequency F0, at which electrons are emitted varies with the type of material, and it is called as threshold frequency. So different material will have different work function. So if they have different work function, they will have different threshold frequency. Okay, how did Einstein explain about intensity? Based on the wave theory, the intensity of the light is related to the amplitude squared of the wave. Einstein explained intensity in a different way when it concerns photons, light that behaves as a particle. Okay, let's consider violet light. So I shine violet light to this metal. You find that photoelectrons will be emitted. Okay, Einstein explained intensity in terms of the number of photons. So in this case, if I consider violet light with low intensity but high frequency. So frequency is related to the wavelength of the light. So since lambda is small, then frequency will be large. But intensity is referring to the number of photons. So we can see that this here, let's consider there's only 2 photons, so intensity is very low. So when I shine violet light with low intensity, you find that photoelectrons will be emitted. So if I use 2 photons, then there'll be 2 electrons emitted. Okay, so if we calculate what's the frequency of this violet light using the formula F, which is C over lambda, we can find the frequency. And when we calculate the energy, we can find the energy of this photon to be 3.10 electron volts. So this energy of this photon is much greater than the minimum energy that's required to produce photoelectrons. Because the minimum that's required will be 3 electron volts. But the photon comes in with 3.1 electron volts. Okay, what happens now if I have high intensity? So it's still high frequency because I'm using violet light, but I have high intensity. So you see there are many photons that's being used, right? So when this photon comes in, what happens is there'll be more electrons that's emitted. But irrespective of whether the intensity of the light is high or the intensity is low, if as long the frequency of the light is high, I will produce photoelectrons. Okay, next consider red light. So red light, let's consider rate of 680 nanometer, and this is the frequency of red light. So if I use low intensity, that means few, let's say 2 photons. When these 2 photons, low intensity strikes the metal, nothing happens. No photoelectrons are being produced. So what's the energy of this red photon? Since we have the frequency, we can calculate the energy of the photon will be 1.82. So in this case, right, you see 1.82 is less than the minimum amount of energy required for photoelectrons to be produced. because the minimum amount of energy will be 3 electron volts. But this photon comes in with 1.82. So the electrons cannot accumulate energy. So it cannot absorb one photon, absorbs 1.82, then absorb another red photon, gain another 1.82, then absorb another red photon, and then eventually comes out. It cannot do that. It either absorbs all the energy of the photon or nothing at all. Okay, we can see, all right, that the electron cannot absorb the photon because if it absorbs 1.82, it's going to take it to the forbidden region. So the electron cannot exist in the forbidden region. So that's why there's no photoelectrons that comes out. Okay, what happens if we increase the intensity? Nothing happens, all right? Simply because the energy of the photon is simply too low. So Einstein explained, all right, intensity is referring to the number of photons. Energy of the photon is related to the frequency of the photon. So it's unlike wave, the intensity of the photon is related to the amplitude square. So intensity and frequency are independent of one another. So you can have high frequency, high intensity, or you can have high frequency, low intensity. So in either case, whenever you have high frequency radiation, then yes, photoelectrons will be produced irrespective of the intensity of the light. When you have low frequency, that is low energy photon, there will be no photoelectrons emitted irrespective of the intensity, whether it's high intensity or low intensity. Okay, question. What's the minimum frequency of radiation to produce photoelectrons in this metal? So when I shine violet light, I produce photoelectrons. When I use red light, nothing. So what's the minimum frequency? So basically minimum frequency will be, to find the minimum frequency, we equate the energy of photon to be 3 electron volts. That means a photon must come in, which is exactly 3 electron volts. Then electrons that has this maximum potential energy of 3 electron volts can absorb this photon and come out. So that's the minimum amount of energy. So from here I can find the threshold frequency. So this is known as my threshold frequency. So even if there's one photon, very low intensity, there'll be 1 electron emitted. Okay, so how did Einstein explain about this photoelectric effect? So when scientists did photoelectric effect, right, they made a certain observation, and the observations were like the effect is instantaneous. So Einstein explained this, and he said that photons are discrete particles of light which carries energy and momentum. So an electron in a metal will absorb a photon if the energy of the photon is sufficiently high. That is, the frequency of radiation must be greater or equal to threshold frequency. Okay, another observation is there's a certain minimum frequency of radiation below which no photoelectrons are emitted, no matter how high the intensity. So Einstein explained this by saying that the intensity refers to the number of photons, not its energy. So if the frequency is less than threshold frequency, no photons will be absorbed, irrespective of the number of photons. Okay, let's look at this example. Intensity here will be referring to the number of cars. So I say, oh, you have very high intensity, right? High number of photons. Energy will be referring to how fast the cars are moving. So these cars can be moving at a very high speed, but very high intensity. So they have case that you have high intensity, high energy. So in this case, I'll say here you have low intensity, but the cars might be slowing down. There was an accident earlier, so they're slowing down to look at the accident. So you can have low intensity and low energy. So they are independent of one another. So it doesn't mean if I have high intensity, energy must be low, or vice versa. Okay, so Einstein explained that intensity refers to the number of photons, not its energy. Okay, the next one is photoelectrons have a range of kinetic energies from 0 electron volts up to a certain Kmax. Okay, how did Einstein explain? So I explained that any electron can absorb the photon. That is provided the threshold frequency is greater, the frequency of radiation is greater than threshold frequency. So when an electron absorbs a photon, it would use part of the energy absorbed as potential energy and the balance as its kinetic energy. Okay, so maximum kinetic energy, all right? So the electron that comes out has kinetic energy from 0 electron volts up to certain Kmax. Okay, so how did Einstein explain about this? Right, let me put this in the form of a table. Let's take, for instance, right, the electron. When I shine light of 5 electron volts, right? So the light that comes in is 5 electron volts. So any of these electrons can absorb it. So let's take, for instance, electron has a potential energy of 3 electron volts. This electron can absorb this photon. So when this electron absorbs this photon, it uses 3 electron volts that they have absorbed to come out. So the balance of its energy will be in the form of kinetic energy. This electron here that has a potential energy of 3.5 electron volts of potential energy. This electron can also absorb the 5 electron volts photon and come out. However, it's going to use 3.5 electron volts of energy to come out. So the balance will be 1.5. This electron, assuming another electron has a potential energy of 4.2 electron volts, if it absorbs this photon, it's going to use 4.2 electron volts to come out. When it comes out with a balance of 0.8 electron volts. Even this electron can come out because it can use all its energy that it absorbed to come out. But when it comes out with 0 electron volts. This electron, right, that has negative 5.6 electron volts will not be able to absorb the 5 electron volt photon because if it absorbs, right, it's going to take it to the forbidden region. But what's interesting is there's a range of kinetic energies, right? It's range from 0 all the way to a certain maximum. So Einstein explained that any electron can absorb the photon provided that the frequency of radiation is greater than threshold frequency. So when an electron absorbs a photon, it would use part of the energy absorbed as potential energy and the balance as its kinetic energy. Okay, next, let's describe how Einstein used the concept of photons and conservation of energy to explain the experimental observation of photoelectric effect and deduce the formula. This is known as Einstein's photoelectric equation, which describes Kmax equals to HF minus W. Okay, let's consider a well. Imagine you have a ball and you're trying to remove the ball from this deep well, all right? So you throw a ball. So hopefully the red ball transfers its energy to this ball, and then this gold ball comes out. But if you use a red ball of low energy, the energy transfer is insufficient for the ball to come out. So what you do is you increase the energy. So increase energy by using a green ball. So when you increase energy, you find that it still doesn't come out because the green ball has insufficient amount of energy. So what you do is you use a higher energy ball, use a violet ball. When you use a violet ball, higher energy, the ball comes out. You are able to catch it at this point. So this is how photoelectric it is, all right? It's like a well, all right, where the electrons are inside the well. So for the electrons to come out, they have to absorb energy. But again, it depends on how much energy do I supply. If I supply a red ball, right, in this case, right, which has low energy, the electrons cannot come out. They cannot overcome this forbidden region. So I have to supply a photon with sufficiently high energy. And only then electrons can come out. Okay, Einstein used the law of conservation of energy. So law of conservation of energy states that the total initial energy equals to the total final energy. So the total initial energy is referring to the energy of the photon. That's what I supply. So the total initial energy will just be HF. The final energy is referring to the electron. Because you see the photon transfers its energy to the electron. So the final represents what happens to the electron. So electron, right, will have potential energy and kinetic energy. Right? So the electrons have potential energy here and kinetic energy when they come out on the surface of the metal. Okay, let's put numerical values, right? Let's say, for instance, the photon has 4 electron volts. You find that this electron that has a potential energy of 3 electron volts can absorb this 4 electron volts photon, right? And it still has a balance of energy. And the balance of energy will be in the form of its kinetic energy. So you see, this is my input energy for EV. My final energy has up to 4 electron volts as well, right? Potential plus kinetic. If a electron that has a potential energy of 4 electron volts, it can absorb this 4 electron volts photon. But when it absorbs, right, it's going to use all its energy to come out. By the time it comes out, it has 0 kinetic energy. Okay, an electron that has 5 electron volts of potential energy will not be able to absorb this 4 electron volts photon because it's going to take it to its forbidden region. So it's not going to come out. So in this case, nothing happens. Okay, if I increase the energy of the photon, right, let's say, for instance, I use higher energy electromagnetic radiation. This electron that has 3 electron volts potential energy can absorb this 6 electron volt photon. It's going to come out. But when it comes up, it's going to have excess energy of 3 electron volts. And the excess energy will be in the form of kinetic energy. So let's consider another electron, 3.51 electron volts of potential energy. This can still absorb the 6 electron volts photon. By the time it comes out, it has 2.85 electron volts of kinetic energy. Okay, let's consider a fourth electron of 3.152 electron volts. It can still absorb and come out at 2.848 electron volts. So what this shows, right, is that the energy of the electron can be of any value because the potential energy of the electrons can also be of any value. So it all depends on what's the initial potential energy. Right? But what's interesting is Kmax. So Kmax is one that's been highlighted here, right? Kmax, right? When I use a 4 electron volts incoming photon, I get Kmax of 1 electron volts. When I change the energy of the photon to 6 electron volts, Kmax now will be 3 electron volts. But Kmax is always related to the work function. The work function, remember, is the maximum potential energy of the electrons. So Kmax is related to the work function. So Einstein rearranged this formula from the law of conservation of energy to Einstein's photoelectric equation, that is Kmax equals to HF minus W, the work function. Because electrons that has the maximum potential energy are the one that's going to come out with maximum kinetic energy. Right? Potential energy.